Today's topic is condition variable. There are many cases where a thread wishes to check whether a certain condition is true before continuing its execution. The example is the case where a parent thread might wish to check whether a child thread has completed or not. This is often called a join. Let's look at the following code. In the main program, parent thread creates a thread. And then there are two print statements. First one is parent begin, and after creating a thread, the parent wants to print parent end. And there's a child thread, and it calls a function child, and function child prints the child statement. So in this statement, what we would like to achieve is we print the three print statement in sequence. The first one is print parent begin, second one is print child, and third one is print parent end, like this. But there is no way for a modern operating system to guarantee its order. So we have to put some function or feature that enables the parent to wait for the child to finish. So the first approach is spin-based approach. Let's look at this example. Here, in the child function, after it prints of child, it sets that done equals 1. And in the main program, first, the main program prints the statement parent begin, and then it calls a pthread create. After creating a pthread and executing a function, it introduces the while loop where it checks whether the variable done is 0 or not. If the done variable is 0, then it still keeps waiting in the while loop. And the variable done is initialized to 0 at the beginning. So unless the child thread sets the done value to 1, the parent threads cannot get out of this loop. Well, this program may work, but it is hugely inefficient because the parent spins and wastes CPU time. So is there any approach or features that allows the child process to wait the parent process or parent threads to wait for the completion of the child thread? So now we are going to learn about the condition variable. Condition variable is actually a queue of threads. So it's a memory variable defined as a queue of threads. There are two important functions. First one is wait, and the other is signal. So the function waiting and condition, there is an explicit queue that threads can put themselves on when some state of execution is not as desired. So that is the queue. And there is another function, signal. So waiting function is executed when there is a function, when the thread calls function wait. And signaling on function condition is called when the caller calls signal. If the caller calls signal, then it wakes one of the waiting threads in the queue and then allows them to continue. So remember, there are three variables in the package. So condition variable C, and state variable, and the lock. So we're gonna learn the details about this. This is the actual declaration of condition variable. Sorry, there is on the bottom. So there is a definition. There is a variable type pthread cond. Okay, so we declare a condition variable C, and of course we have to initialize the condition variables. Whenever you define a variable, you should not forget to initialize it. And there are two important functions. There is pthread and the cont and the wait, and then signal, There are two functions. What you should not forget is when we call the wait, it has two parameters. First one is condition variable, and the second one is mutex. So you should not forget that. For a signal function, it gets one parameter. It's a name, the condition variable. When a signal function is called, the pthread library wakes up one of the thread that has been waiting for the condition to become true. So the wait core takes the mutex as a parameter. Then the wait call releases the lock and puts the calling threads to sleep. When the thread wakes up, it must require the lock. So that's the important part. And then we're going to deal with the actual code and going to explain what these mean. Let me explain the actual code. In this code, a parent is waiting for the child to finish, and we implement it using a condition variable. There are three functions. First one is thread exit, and second one is child, and third one is thread join. Thread exit is called by the child when it finishes execution and when it wants to allow the parent to process. There's thread join, and thread join is called by the parent and it waits for a certain thread to finish its operation. So this is how it works. First, there is child, and then when it prints a child string after calling printf, it calls thread exit. Okay, and then in thread exit, it first locks the mutex and update the state variable, and then calls condition signal and unlock the mutex. There are basically four functions. And for thread join, it is called by the parent thread, and it allows the parent threads to wait for the completion of the child thread. So when you call thread join, it first locks the mutex, and then if done is zero means that parent has to wait for the child to finish, and then it calls thread condition. First one is condition variable, second one is mutex, and then it calls pthread mutex unlock. And then this is the main body of the function. So first it prints the parent begin statement, and then it creates a thread and executes a thread function, and then after creating a thread, it waits for the child thread to finish by calling thread join. So this code works perfectly. And let's deal with details of the code. From the parent point of view, the parent executes as follows. It first creates a child thread and continues running. And then it calls thread join to wait for the child thread to complete. So inside thread join, it acquires a lock and check if the child is done, and then put itself to sleep by calling wait, and then releases the lock. This is how it works. For child, it prints the message child and then calls thread exit to wake up the parent thread. Inside thread exit, it grabs the lock, sets the state variable done to 1 and signal the parent and waking up. So we need to have three variables for a condition variable. First one is condition variable, second one is state variable, and the third one is mutex to protect the state variable. Protecting state variable. Okay. So then what if we do not use state variable? What if we do not use state variable? Let's look at this situation. There's two functions, thread exit and thread join. In thread exit, it locks the mutex and generate condition signal and unlocks it. And their thread join, and it waits, called mutex, lock the mutex and calls condition to wait, and then unlock the mutex. Okay, so here, different from the code I've shown before in the previous page, here there is no state variable. There is no state variable. So we used to have done variable to represent the state of the system, whether child has finished or not, but we do not have state variable here. Then what is going to happen? Imagine the case where the child runs immediately. Then the child will signal, but there is no thread asleep on the condition. Okay. Then when the parent runs, it will call wait and will get stuck. And there's no thread to wake up the parent thread. So without state variable, there's no way for the application to denote whether a child process has finished or not. So in case there are two threads, child and parent, and somehow if the child executes first and then before the parents go into sleep, then there's no way for the child process to wake up the parent thread because child process finishes before parent process going into the sleep. So that's why we need a state variable. This code is subject to race condition and thus incomplete. Let's consider the following scenario. The parent has called thread join. So it executes, it checks if done is 0. And it finds that done is 0, so it is going to sleep. But somehow the parent process is interrupted. And then child process going to execute it. And then it changes the state of the done to 1. And then it calls, it signals the parent. However, unfortunately, the parent process has not gone into the sleep yet. So after executing number 3, then let's assume that the parent gets the control again. It runs again. Then it gets 4. And then when the parent thread has gone into the sleep, there's no thread to wake it up. So parent is going to sleep forever. We'd like to examine the producer-consumer relationship problem. A producer produces data items, and it wishes to place the data items in the buffer. And consumer, it grabs the data items out of the buffer and consumes them in some way. So there are two threads. And this is producer. This is consumer. And there is a buffer shared by both of the threads. And producer creates an item and put it to the buffer. And consumer grabs the contents in the buffer and consumes it. But if the buffer is already filled, then producer cannot produce as an item. And consumer, if the buffer is empty, it cannot consume the contents. So the example of that kind of application is multi-thread web server. The producer puts HTTP request in a work queue, and consumer threads take requests out of this queue, and processes them. Bounded buffer is used also when you pipe out one of the programs into another. For example, it's a grep statement, grep foo file.txt. The meaning of the grep is find a string foo within a file.txt and count and feed the result of this statement into the command wc. wc is word count. word count. So here, the grep process is a producer, and word count process is a consumer. And between them is an in-kernel bounded buffer. It is important that buffer is in the kernel. Bounded buffer is shared resource. And so the two threads, the producer thread and the consumer thread, has to be synchronized to properly access the shared buffer. The first version of put and get routines. There is buffer, and there is count, and there is put function that puts the value to the buffer, and get functions that retrieves the value from the buffer. There is a assert function, check if the buffer is full or not, and there's another assert function if the buffer is empty or not. And it put function, it first checks the buffer is full, and then sets the value of count to 1, saying that the buffer is full, and then it sets the value to the buffer. In the get function, it checks if the buffer is empty or not, and if it's empty, then it stops. But if it's not empty, then it returns value from the buffer. Of course, this function is broken because there is a put and get function, and put function, there's going to be multiple producers. In generality, there are multiple put threads. This is executed at producer. And there's going to be multiple threads also, and there's multiple consumers. And these consumers and producers will share access the shared variable count. Okay, so producer thread sets the value of count, and also the consumer thread sets the value of count also. But as you can see, we do not have any access control over the access to the count. Let me put an example. There's 1, 2, 3 lines, and 4, 5, and 6. Let's assume that producer 1, producer 2, consumer 1, consumer 2. For example, the producer 1 executes the first statement, then check that buffer is empty. So the producer 1 is going to place a value to the buffer. But at the same time, the control is transferred to the producer 2, and it checks also that count is 0 or not, and finds also that buffer is empty. And in both cases, the producer 1 and producer 2 is going to put a value to the buffer. So the race condition is going to happen. So something like that has happened. For example, there are 2 consumers. And then the first, for example, in the second example, another example is, let's forget about this situation here and assume that currently buffer is full. So the producer, instead producer, the consumer 1 executes the statement fore and finds that buffer is full, and it is going to retrieve the value from the buffer. But right after executing the line number 4, the control is transferred to the consumer 2, and it also executes line number 4. In that case, both of the threads find the buffer is full, and one of them is going to read the buffer first and retrieve the value, and the second thread, second consumer, it has to read the value from the buffer that has been already consumed by the preceding consumer. So essentially, it reads the empty buffer. So, as we have observed here, we do not have any synchronization mechanism in this code. So we're going to put the synchronization mechanism so that the producers and consumers wait for each other to fill the buffer and to empty the buffer. So this is the actual version of the producer. So producer spinning in the loop, and it puts the value for loops number of times. And consumer thread reads the buffer as long as there is a data in the buffer. So this is the first solution. Of course, this is broken, but this is the full solution about a producer and consumer relationship. This is producer. And it protects access to the count variable using the mutex, and it waits for the consumer to consume the buffer with condition variable. So there is single condition variable and there is if statement. Let's look at the code. The for loops iterates loop number of times and it puts the value to the buffer. However, there is a statement that protects the access to the shared buffer. The first, before it access, it reads the count and checks if the buffer is full or not. It acquires the mutex so that the access to the count variable is each exclusive. And if the count is 1, which means that buffer is already contains some value, then it puts itself to the wait state. And then in that case, it calls pthread cont wait. And there are two parameters. First one is condition variable. The second one is mutex that is used to protect the access to the count variable. Once this is done, so once the threads gets out of the wait, then it means that condition has satisfied. Now it puts the value to the buffer. After it puts the value to the buffer, it signals the queue that the data is ready in the buffer. And after making a signal, it unlocks the mutex. So that's the basic skeleton flow of the producer threads. The code for the consumer thread is similar. First, it acquires a lock on the mutex and check if count is 0 or not. And if count is 0, then it means the buffer is currently empty. So the consumer thread has to put itself to the sleep, waiting for the buffer to be filled. And then after getting out of the condition wait, it gets the value from the buffer. And after it gets the value from the buffer, it informs the other threads that data is empty, the buffer is empty. And then it unlocks the mutex and prints the value that has been retrieved from the buffer. So that's the basic skeleton structure of the consumer thread and producer thread. Okay. It looks okay, but what if we have more than one producer and one consumer? Let's look at this scenario. We have now two consumers and one producers. There's buffer, there's the ready queue, and there's sleep queue. Now, consumer thread executes first. It finds that buffer is empty. Now, it puts itself to the sleep queue, like this. So C1 is now in the sleep state. And then the thread P1 executes and it puts the value to the buffer and sends the signal. And C2 just arrives. Now the P1 has sent the signal and C2 has arrived, and then it finds that there is a contents. So P2, there's a buffer, contents in the buffer, and C2 is in the ready queue. Okay. Now, now C1 gets signal here. So since C1 gets signal, C1 is going into the ready queue, because now C1 has received a signal from the producer, then there is contents in the buffer. So it goes into ready queue. Now C2 gets executed and C2 consumes a buffer and it reads the data from the buffer. And then C1 just has got out of the sleep state and it is going to be executed now. And of course, as P1 is waiting, P1 is waiting in the sleep state for the buffer to be emptied. Now, then C1 reads the empty buffer. Okay. So the problem is, according to the previous code, C1 blindly reads the buffer after it gets waken up. Okay. The source of this problem is because of the if statement. Let's get back to the code. This happens between the change in the state of the system. There's T1 and there's T2. And the consumer threads get waken up at T1. So C1 gets woken up. And C1 gets executed. So when C1 wakes up, the buffer was empty. And when C1 gets executed, buffer is full. So there is a difference between the state of the buffer when it gets wake up and it gets full. When it gets executed. All right. But so in this code, after it gets out of the loop, it blindly executes put statement. That seems not unreasonable, but in reality, at the time it gets wake up and at the time it gets actually executed. Here, the consumer is in the ready queue, like this. Here, the consumer is in the CPU, and there is time difference between T1 and T2. The delta is not 0. So between this time period, the state of the system, state of the buffer has changed. So what are we going to do? The solution is simple. So the solution is very simple. Puts while instead of if. That's very simple. So after consumer wakes up, it rechecks the system, the state, if the condition that has been held when it has received the signal still holds at the time it gets actually executed. So it finds that buffer is empty, then consumer simply goes back to sleep again. So we have to replace if with while. So let's repeat. The problem arises for a simple reason. After producer woke consumer 1, before consumer 1 ever run, the state of the bounded buffer changed it by consumer 2. So in the current operating system, there is no guarantee that the woken thread run state will still be as desired. So this is mesa semantics. So in modern operating system, virtually every system ever built employs mesa semantics. But there is another semantics, fore semantics. It provides a stronger guarantee that woken thread will run immediately upon being woken up. So this fore semantics is stronger and it's simple. However, it is very difficult to implement an operating system that has fore semantics. So virtually all operating system employs mesa semantics. Okay, so this is how we solve the first problem. We replace if with while. However, this code still have a problem. Let's look at what it is. Okay, again, there are 3 threads. There are 2 consumers and 1 producers. And there is buffer, and there is ready queue, and there is sleep queue. There is 2 consumer and there is one producer, and there's buffer, and there's ready queue, and there's CPU, and there's sleep queue. Okay, let's start. Consumer executes first, and then because it finds the buffer is empty, so it puts in the sleep queue. And then consumer 2 executes next, and also it finds that buffer is empty. So there are two threads in the sleep queue. Both of the consumer threads are in the sleep queue. Then the producer executes and sends a signal. The producer executes and sends a signal. Okay. So producer puts contents in the buffer and sends a signal. And then puts itself in the wait queue because the buffer is full. So now there are 3 threads in the sleep queue. But of course, one of the 2 threads, consumer 1 and consumer 2, will receive the signal from the producer and will get wake up. Here, the C1 gets the signal and executes and consumes the buffer. So C1 executes and consumes the buffer. And of course, after it consumes the buffer, it sends a signal. C1 sends a signal. And there are 2 threads in the sleep queue. Somehow, however, C2 gets signal. Okay. Then what's going to happen? C6 gets executed, but it finds that buffer is empty, and it goes to sleep. Okay. Now C2 is going to sleep, so there are again 3 threads in the sleep queue. P1, producer 1, producer consumer 1, and consumer 2. So even though buffer is empty, and technically producer should be allowed to proceed and should be allowed to create the contents to the buffer, there is no threads to wake the producer up, and all the threads are blocked in the sleep queue. So why does this happen? The reason is that the signal created by consumer 1 means that buffer is empty. So that signal should have been received by producer, not by the consumer. So P1 should have gotten the signal from the C1. However, C2 gets the signal. So that was the problem. So how can you solve the problem? Well, we have to use separate signal, separate condition variables. That's the key. So in actuality, producer and consumer waits for the different condition of the system. Producer wants the buffer to be empty, and consumer wants the buffer to be full. So we have to introduce separate condition variable for both of the conditions. So producer now waits on the condition empty, and when it finds the buffer is empty, then it generates the contents, and at the next it signals the condition variable fill. Consumer does the opposite. The consumer threads wait and fill and signal empty. So this is how it works. So this is producer code. So producer locks the mutex to check if the counter is 1 or not. And then if it's 1, then it has to wait. After it creates the contents to the buffer, it generates a signal, but this time the condition variable it signals is fill. Okay, so here the producer waits the buffer to be empty, and then once it's empty, then it generates the contents and it signals the buffer full. Consumer does the opposite. In consumer, it waits for the buffer to be full, and once it's full, then it consumes the buffer and it signals that buffer is empty. So this is complete solution. Right? Happy OS. Okay, so this is more generic solutions. So assume that so far we can only save one contents in the buffer. So if the buffer is full, then producer has to wait. And because there is only one content in the buffer, if it's consumed by the consumer, then no more consumers can consume the values from the buffer. So we would like to introduce more concurrency to the number of threads. So we're gonna add more buffer slots to allow that there is concurrent productions and concurrent consuming to take place. And this is to reduce the context switch as well. Here, so now the buffer is an array of integer, and there is fill count, and this is use count, and there is count. Okay, so this is circular buffer, as you might already familiar with. So this is circular buffer. Okay, and there is a count pointer that points to the slots where you need to put a value, and also there is another pointer that points to the slot where you can read the data block from. So there is fill pointer and use pointer. And then input function, it places the value to the fill slot and advances the pointer by 1 and increase the counter. So count is the number of contents in the buffer. And there is temp variable, and it increased the use by 1. And then it decreased the number of contents in the buffer and decreased count by 1 here. So fill process and use process distractions. So there is contents, some contents, some contents, some contents. Okay, this is how it works. So for producer, producer has to check whether the count reaches its maximum count or not, right here. So if the count reaches maximum, which means the buffers are completely full, then it has to wait. And if it's full, then it has to wait. Some of the slots become empty. And then after it putting some materials, it has to signal that there is contents available in the buffer, and then it unlocks the mutex. Likewise, consumer did a similar thing, but in the opposite way. First, it checks if the count is 0 or not. It means that the buffer is completely empty. If the buffer is completely empty, then there's no contents to consume, so the consumer thread has to be put into sleep, waiting for some contents to be created in buffer. So it has to wait, and after it gets out of the sleep, it consumes the contents from the buffer and signals that there is some empty slots available in the buffer. Okay, so this is final working solution. A producer only sleeps if all buffers are currently filled. And a consumer only sleeps if all buffers are currently empty. Okay. So one last topic. This is covering conditions. Consider the following scenario. This is kind of malloc situation. Assume that there are 0 bytes free. So thread A cores allocate 100 byte. So there is threads A and it wants to be allocated a size of 100 byte. There's another thread B, and it wants to get allocated a 10 byte chunk. But currently, it's empty. The memory pool is empty. There's nothing in it here, so both thread A and thread B has to be blocked and go to sleep. And then there is thread C comes, and then it has returned a size of memory chunk size of 50 bytes. This is 50. Okay. Now at some time, now the size 50 memory chunk is available. Okay. But there are 2 threads in the sleep queue, and so which thread the operating system or the condition variable library has to wake up? Of course, it has to wake up the thread B, because if we wake up thread A, then currently we have only memory chunk of 50 byte large, and TA has requested a memory chunk with 100 byte. So if we wake up thread A, then thread A is going to go to sleep again after it checks that the given memory chunk cannot accommodate my request. However, here there is no way to examine the size of the request for each thread. Sleep queue is the queue of threads, and it does not have any information about the condition it has requested. Okay, so to make this simple, we have to introduce, this is actual code. Let's brief look at the code for covering condition here. There is function allocate. It first acquires mutex, and it checks if the bytes left is less than the size. Then if there is not enough memories to allocate, then it has to wait. Okay. And then after it gets out of the wait condition, it gets allocated appropriate memory chunk, and then bytes left decreases by the amount of data block that has been returned to the user or caller. And then it unlocks the mutex. On the other hand, for the free function, it first locks the mutex, and then because it frees a certain memory chunk, it increases the bytes left by the memory chunk size. And then it sends a signal to wake up some of the threads. And then it unlocks the mutex. But the problem is right here. So when you send a signal, to whom do you have to send a signal? Okay, there is no way to identify which one you have to send a signal. To solve that problem, Lamson and Riddell has proposed a new primitive in the condition variable, which is pthread cont broadcast. It is literally a broadcast. Pthread cont broadcast wake up all the waiting threads and put it in the wait queue. Okay, so if there are three threads in the waiting in the sleep queue, if the caller calls pthread broadcast, then all the 3 threads are put it in the ready queue and waiting for to be executed. The cost can be prohibitive, of course, because if there are many threads waiting in the sleep queue, then covering condition, the pthread cont broadcast will wake them all up. So too many threads might be woken up. The thread that shouldn't be wake up will simply wake up and recheck the condition and then go back to the sleep. So using the pthread cont broadcast, we can solve the problem we have observed in the malloc situation. That is called covering condition.